Hi all, and welcome to the Medical AI Lab session. Today I'm delighted that we have Kathryn Wantlin presenting to us on meaningfully debugging model mistakes using conceptual, counterfactual explanations and more. So without further ado, Kathryn, take it away.
Great. Can everyone see my screen? Great. Yeah, so I'll be talking about a quick summary of two recent works on identifying and mitigating model failures, which are particularly important in the medical AI domains. So yeah, the first one I'll be talking about is the meaningfully debugging paper that came out of Stanford. And then a second very related paper on distilling model failures as directions in latent space from MIT. Cool. So just to set the stage for the key questions in model evaluation that these two papers tackle. So they're trying to ask the question, so if you're given an image misclassification, can you understand anything about was this kind of image underrepresented in my training distribution? Did I pre-process incorrectly? Or has my model learned some spurious correlation or bias that's hindering generalization in my test set? Trying to figure out interpretable tools to be able to correct for these kinds of mistakes. So the first paper that I'll talk about takes the approach called Counterfactual Conceptual Explanations, called CCE. The headline for it basically being it's using human interpretable concepts, trying to understand what perturbations to the input based on these concepts are needed for the model's prediction to change in a particular way, more specifically to change to be the correct label. So some key advantages of this particular approach is that there's no training data or retraining needed. It only uses the model needs white box access, so it needs to be able to know what those layers are, but doesn't need to actually change anything about the model. And then for the human interpretable concepts, they can be learned with any data set. Doesn't have to be the training data that you use to train the model itself. And lastly, provides high-level explanations at the level of human interpretable concepts. That makes it easier for machine learning practitioner to understand what aspects of the model are failing. The key related work for this paper and also quickly for the next paper are this idea of concept activation vectors, which are basically SVMs trained at the concept level. So just linear classifiers, they're going to be trained in the bottleneck layers of the network. And they are supposed to correspond to concepts. They're either user defined or automatically discovered. And we'll talk a little bit more about how we get those vectors. So this paper, CCE, basically extends CAVs by showing that the perturbation that you get along a CAV can be used to change the model's prediction. And isolating exactly what those changes are supposed to be is basically what CCE's algorithm is training for. So a quick overview of the method of this paper. So the first step is we just need to get like a concept library with which that we can basically perturb misclassified images down the line. This concept library can kind of come from either prior works. You can learn them automatically, or sometimes they have been like pre-designed for certain data sets. So it's up to you. Lots of these are sort of readily available. And then you can learn this concept activation vector, basically an SVM, for each concept at your embedding level of your model. So you have all these vectors, for example, for stripes, for cows, for water, for field. This yellow box on the left, you can see the decision boundary, the SVM that's been trained for stripes in the embedding space. So secondly, once you have these vectors, now you have like a misclassified example, which is this zebra down here. This boundary isn't the same like as the CAV boundary. It's just like some boundary that exists in the embedding space. between like the African hunting dog label and the zebra label. So it's not like a boundary between concepts. Yeah, this zebra is on the wrong side of the decision boundary for its label when it wants to be over here instead. So given this misclassified example, we would like to generate the conceptual counterfactual, aka what concepts, if they had shown up in the embedding space for this zebra, would have pushed it over the line to the correct space to be correctly labeled as a zebra. And this is some sort of weighted sum W of your concept bank big C that has been basically pre-processed from all these little C's in step A. And then lastly, you can basically kind of look at the scores that you're getting in that W vector. And you can see here that if there had been much more stripes, if stripes had been much more prominent, the score for that is very high. Then we would have been better able to identify that this is a zebra. So a larger positive score basically means that if you add more of that concept to that image, it would increase the probability of having correctly classified that image. And then sort of the flip side for removing concepts from images. Great. So sort of diving into more specifically the math behind this algorithm. Some quick notation, the neural network model is denoted as F. The bottom of the network, basically what gets us to our embedding space, is denoted B sub L. And the top of the network that gets us from the embedding space to our K labels is T sub L. So the two steps here, of course, are learning the concept vectors first, the algorithm for that located on the right, and then we run the CCE algorithm. So learning the concept vectors seems like a lot of text, but it's basically pretty straightforward. So we're using these SVMs. We divide our network into the bottom and top. And then for each concept, which has been sort of chosen beforehand, we basically just learn an SVM for that concept in the embedding space. And then for concepts, which we don't think we learned very well, depending on some threshold, we just ignore those, focus on the ones we're very confident on. So now you have your CAVs. Now you would like to know what linear combination of your CAVs would you like to have for certain misclassified examples to be able to have them classified correctly. So the different parts of this optimization problem, first for correctness is this red part, just the cross entropy loss. Basically between this B is applying the bottom vector or the bottom of the network to a particular input to get to like the bottleneck embedding space. And then you're adding some linear combination of your concepts, W times C. And then you're applying the top of your network to get some label distribution. You're just computing cross entropy loss. So you're just trying to minimize this loss to get your label to the correct side. The other like desirable feature of this is that we would like our W's to be more sparse because we would like to sort of interpret from fewer concepts rather than more concepts. So this like elastic sort of regularization is happening here. It's just like a linear combination of L1 and L2 regularizations. So that sort of enforces the sparsity side of things. And then lastly, this important piece that sort of distinguishes it from some similar works that rely on decision boundaries is this validity constraint. So there's like basically two sets of constraints for each of Wmax and Wmin. So I'll just talk about the Wmax ones. They're very similar for Wmin. So the first one basically says that we generally should not be able to add more of a concept that's already present to explain the model's mistake if that concept is already in the image. Like if you're seeing a cat on a bed and the bed is already very prominent, maybe adding more of the bed concept would not help you to understand that it's a cat, even though that's sort of maybe like a spurious correlation example. You can also relax this idea by basically setting this kappa to be something positive. So if it's 0, it basically says that, so this is just the this like C times B plus V is basically just the size of the margin itself. So if that concept shows up at all, if kappa is 0, you basically just want to say that you don't want to add at all any of this concept at all. And you can relax that by making this something positive. The other validity constraint is that maybe we don't want to like add infinite amounts of some concept. So we just like cap it at some maximum margin that we've seen over the training examples. So combining all of that, driving the same thing for W min. The rest of this algorithm just proceeds via gradient descent and then just clamping the W between these two values until W has converged. So this is the optimization problem. So that's the summary of the methods. So now I'll just talk about results. So first, we just wanted to understand, does CCE accurately or precisely identify the correct spurious correlations that are happening in certain images? So they chose some particular examples. The ones here are dog correlated with snow, cat correlated with bed, and bird correlated with sand. So they ran like 3 different experiments, random, CCE control, and CCE. CCE is where we explicitly correlated, or they explicitly correlated dog with snow. CCE control is where there was no spurious correlation added. And then random is where they sort of just randomly chose some images from their image data set. So there's sort of the 3 experiments that they ran for different combinations. So for CCE control, as expected, there shouldn't be any identification of spurious correlation because they didn't specifically design for that. If those correlations are happening randomly, they're sometimes going to be picked up just by chance. But if you apply the CCE algorithm, I think basically for 100 or more than 90% of your test examples, for most of these cases, you're going to be able to identify that the correct concept is being correlated with that particular label. And then this chart is basically sort of summarizing these results and also comparing them across some different algorithms, most notably COCO-X, which is probably the most similar in that it uses fault lines, I believe it was called, to do this like disambiguation. So the mean precision 3 is basically trying to see if does the correct spurious concept show up in the top 3? And it also looks at the rank of the concept among the top 150 total concepts that were chosen. And generally, you can see here that the precision is the highest for CCE, and then the rank for the correct the rank of the correct spuriously correlated concept is highest, or the number is smallest for CCE. So it is outperforming some of those related works. We also did some just like qualitative investigation into sort of like the degrees of correlation that you might observe. So on the left, the experiment they were running here is they had a model that was trained on to identify apples, but they only showed it examples where the apple was in grayscale. They were basically trying to see, if we removed greenness from a test image of this apple that is in color, and we just gradually move it into grayscale, is that going to help us, first of all, to predict that it is indeed a Granny Smith apple, which you can see on the black line. And then also you see the CCE score also increases correspondingly, as it's better able to detect the spurious correlation that's starting to show up as you grayscale out. Also on the left, they wanted to sort of understand, are our validity constraints actually helping us? So basically, so I mentioned like the cat and the bed example. In the middle, So I think it thinks that it's a bear. So if you did CCE with no validity, the bed would be a concept that's ranked much higher, versus with full CCE, it'll be ranked much lower, so at 137 rather than 3. And then similarly for different pairs of class and concept. Lastly, they ran some experiments actually with medical domain data. The first of which is a dermatology data set. So you can see also some of these bars for 4 different examples in a dermatology data set. So you can see that it struggles maybe with the zoom of the particular image if there's hair present. For some of these also, darker skin seems to make it harder to correctly classify. So we might have some like racial biases in our data sets. So they took like a qualitative look as well for dermatology. And then lastly, they also did, oops, sorry, that should say just cardiology on the top. So they looked at chest x-rays. They were trying to understand if different views had an effect on the label that we were getting. So we provided like several lateral and frontal views for this particular data set, as you can see here. And then for the Stanford data set, it has both lateral view and frontal view. But this model that they trained it on only saw frontal view examples from an NIH data set. So they took like 150 images of lateral view, and in 100% of those images, the CCE model was able to identify that the lateral view concept had like the highest negative score, meaning that if we decreased the prominence of lateral view in this image, then it would have been better able to classify it, aka we needed to see more images from lateral view. So it's a practical example of how users can identify shortcomings in these models. Yeah, and sort of the other very related work also in the space of interpretability for model correction is this distilling model failures as directions and latent space work. So they also take an SVM approach, but it's slightly different in that it doesn't rely on concepts itself. So basically this sort of sets up, this visualization sets up the motivation where we have in the embedding space some decision boundary between correct and incorrect examples for a particular class. So right now we're looking at the class of like old versus young. Basically what this, what they're trying to show here is that because of the way that the data set was constructed, there are many more examples of young women and old men, but not very many examples of young men or older women, which makes those particular examples hard exemplars, so it's harder to classify. So they'll be like boxed in red as incorrectly classified. So basically the spurious correlation of age and gender is existing. And so the decision boundary that has been learned is relying too much on male or female to be able to understand old or young. So this paper is trying to understand how can we disambiguate between these. So instead of using concepts, they essentially just look at the latent space and they featureize and rely on sort of image and text classification in conjunction. So they say that basically the latent space of the original neural network might not always be a good choice because it has overfit possibly during training. So some of the correlations that exist there and the features might not be present in the test set. So we want something that is more like data set agnostic. And for this purpose, they use CLIP, which is a recent contrastive learning approach. So it embeds both images and natural language into a shared latent space. And since the language is embedded in the same space as the images, it basically allows us to automatically assign captions to directions extracted from an SVM that is learned for a particular label, and basically identify, okay, if we have overall for this class, if we're looking at old versus young, then maybe on like the young side of the boundary is sort of like the secondary text label that we're going to generate on this side of the boundary, going to be something related to woman or girl. And then similarly, for the older male side, or for the older side of the boundary, are we going to get labels, embeddings that are very related to being male? So that's kind of the idea of the advantages of using CLIP here. So they focus on like 3 sets of sort of evaluation criteria. One, just being able to show that the SVM decision value, aka the distance from each embedded example to the SVM decision boundary, if that value gives you like a better tell of possible spurious correlations or other aspects of the data set that are not helping us to do classification, is the SVM approach doing better than just models confidence? So this diagram is basically showing for celeb A, they're ordering it either by the SVM decision value or by the model's confidence. And then for each cutoff, basically showing that the SVM approach is better, there is a higher fraction of the spurious correlation text embedding vector compared to the model confidence approach. And that's also shown for both class old and class young. Also, another way to just show that their approach was valid, basically they varied the degree of spurious age-gender correlation and showed that basically as that increased, you got like a better SVM cross-validation score, which is basically just saying that if you have more gender correlation there to like help you learn that boundary, your SVM might have like a higher validation score because it's relying more on gender to learn the old-young difference. So that's just sort of establishing the correlation between those two ideas. And lastly, just some like examples if for the celeb A data set, showing here the hard versus easy exemplars and the correlation between older men or older women and younger men being harder to classify. Sort of the last aspect of this paper is they wanted to show that there was a suitable way based on these SVM decision values to essentially help to retrain a model to improve its accuracy scores. So basically here, the key thing to look at is the 3 model types on the left, so either the base model, which has not been retrained, and then 2 different retraining strategies, one being the Oracle upweight, and the other being the SVM upweight. Depending on the data set, I think they usually just take like some K examples from each class that have like a really high decision value, and then just add those back in to do retraining. And basically this is just showing that the SVM approach is very, gets you accuracy numbers that are very close to if you had used the optimal, which is the Oracle upweight. So the SVM approach is giving you a very good tell. Yeah, so just quickly running through some other tests they ran. So the first set was just identifying spurious correlations. You're going to see like a set of like very similar results if you're looking at cases where you have underrepresented subtypes. Like for example, the results shown here are for CFAR 100, where basically you have a superclass and then 5 subclasses underneath. So they're looking for like a particular superclass. If we purposely remove one of those subclasses, is it going to pick up on that minority subclass more more than using the SVM approach versus the confidence approach. So this is very similar to the graphs you saw for CFAR 10. And then on the right, basically you see the results of doing the adding examples back in, either using the SVM decision value or using the confidence value. And the SVM decision value gets you higher accuracy. And the last sort of set of experiments they're doing is just showing that even with novel subpopulations, so not ones that we are already aware of or that we artificially create for, can we also still identify those? So here we see some examples where there are biases with respect to color and location. So it seems to be better able to identify like white dogs and cats that are indoors. Yeah, and then for CFAR 10, if very similar to, this is just the re-adding in of the top, I think, 100 examples for CFAR 10, if they added those back in and then retrained, the SVM decision value method gave you the highest increase in accuracy over just using model confidence or randomly adding images back in. And the last set of examples are medically relevant. So you can see here qualitatively, the representative images flagged by this SVM as the most incorrect are generally blurrier or less bright. And this sort of trend is not reflected if you're just looking at the confidence scores for this image, for these images, indicating that the SVM framework is isolating a different trend than if you just use model confidence. Yeah, so this is the last result from this paper. So they noticed that for chest X-ray 14, there was sort of like a difference in some of the ways that the radiographs were being taken. So they could either be posterior anterior or PA radiographs or anterior posterior or AP radiographs. So the PA radiographs are usually better, but they require the patient to be well enough to stand. If not, then they would rely on the AP, which is the version that we're seeing the results for here. So basically, figure 13 is looking at one particular class called no effusion and is looking to see if there is some correlation with the AP position. So basically, the SVM method for this class flags a large number of the AP radiographs as incorrect, which basically says that the model might actually be relying on the position of those radiographs to be able to predict whether the patient is healthy, aka maybe the way that we've taken the picture is telling us something about like the health of the patient that isn't just from the actual chest image itself. And moreover, the SVM also selects these AP examples much more consistently if you look at the ordering chart that we've seen before as well. So it's better able to pick up on those than the confidence method. So yeah, that was kind of my last slide for this. Thank you.
Thanks, Kathryn. Really fantastic presentation.